Hello and welcome to another one of D's ADD videos. Today we're going to have an example of a non-separable differential equation in which you have to use an integrating factor. So again, the typical format is going to be one of these guys, and you always have to make sure that your coefficient of your dy dx is equal to 1, and if it's not, divide it out. So my example I'm going to do, it's going to be relatively simple. I don't want to bog you down with too much mechanics. Just kind of illustrate the flow of how the problem should go. Let's see, what do we want on this side? Let's do an e to the 3x. Okay. So first off, you should notice that there's a 2 right here that should not be there, so we're going to divide everybody by 2 or multiply the entire equation by a half, however you want to look at it. So I'm going to divide this one by 2. Of course they're going to cancel by 2 by 2. Okay. So my new equation then becomes dy dx plus 2y e to the 3x over 2, and now I'm ready to find my integrating factor. If you remember, the integrating factor mu is equal to e raised to the integral of p of x dx. And if you remember, p of x is going to be the coefficient of whatever y is. So in this case, it's going to be e to the integral of 2 dx. The integral of any constant is that constant times the variable to the first power. So our integrating factor mu then becomes e to the 2x. Don't need a plus c because we're not actually integrating the problem. So now what you do is you take that integrating factor and you multiply both sides times that integrating factor. So the left side had a dy dx plus 2y, and then the right side was 1/2 e to the 3x. So when I distribute that e to the 2x on both sides, let me just go ahead and do it like this. The left-hand side, if you've seen the conceptual video, always is going to be the derivative of e to the 2x, which is my integrating factor, times y. If you were to go off to the side and do the derivative using the product rule and implicit derivatives of this times that, the integrating factor times that, you would get this answer up here. So just as a quick proof, the derivative of e to the 2x is going to be 2 e to the 2x. This is not part of the problem. It's just to show you that indeed what I just said is true. And then plus the derivative of, first we write the e to the 2x without changing it, and then the derivative of y is 1. Since it's derived with respect to x, we have to put a dy dx there. And you can see if you factor out that e to the 2x that's common to both of those, leaving you 2y plus dy dx, that indeed you have that staring you in the face right there. Okay, so what you can do as a rule of thumb is whenever you get to this step where you multiply both sides by the integrating factor, the left hand side is always going to be just the integrating factor times your y. So here's my integrating factor, there's the y, and you put a d dx in there to let the person know that you know it is, these two are equivalent. The derivative of the integrating factor and y is equivalent to this whole expression up here. Okay? The beauty of that is that whenever you integrate both sides, this side just cancels out and you will be This was the side note, right? Not part of our problem. You'd be left with the integrating factor times y, and that's every time you do these problems. Okay, and then on the right hand side we had the integral of I'm going to bring that 1/2 because it was e to the 3x over 2, right? And then we have e to the 3x times that e to the 2x integrating factor. And if you remember your algebraic rules, whenever you have two like bases, in this case we have two e's that are the same, and we have multiplication as our process that we're doing here, you add the exponents. Still haven't integrated, still need the integrated sign. This whole side just comes along for the ride. And then at this point we can integrate the right hand side. If you remember the off to the side rules are typically in red. E to the number box, d box, whatever your box variable is e to the number times the variable. As long as that variable is the first power, this rule holds over the number. What you're doing there is a u substitution. It's a shortcut rule so that you don't have to do a u substitution for the basic ones. So in our scenario, the number is the 5 and the box is the x, right? So we have 1/2 e to the 5x over 5 plus c. And here we have e to the 2xy. If you remember, the next step is to get y by itself. We want to have an explicit solution if at all possible. And then that would be times 1 over e to the 2x on this side. So here we have y equals 1/10 e to the 5x times 1 over e to the 2x plus c over e to the 2x. And here we have two like bases and they're being divided, right? If you just were to multiply that across and that one across, they'd be divided. And that's a 5x over 2x, so you'd subtract the exponents. And you get 1/10 e to the 3x plus c e to the 2x equals 1. Okay? Again, this is your general solution. Let's say I gave you y of 0 equals it doesn't matter. Let's do 11/10. Again, this one is your x inside the parentheses, this one is your y value. You plug in, solve for x, so we have 11 over 10 equals 1 over 10 e to the 0 c over e to the 0. Anything in the 0 power is 1, so that becomes a 1, that becomes a 1, and you're left with 11/10, 1/10. Let's see, which if you subtract that 1/10 over, you get 10 over 10 equals c, which that's a 1. So the final stage to this problem would be to plug into your general solution, which was right here, if you remember, and we solved using these initial values that gave us this particular solution. So the only thing I'm going to be doing here is just plugging in for this c value. So we're going to have the final solution be y equals 1/10 e to the 3x plus 1 over e to the 2x. Okay? Again, you can get tripped up over integration rules if you don't take your time to do these properly. Don't forget to make sure that this coefficient is a 1. If it isn't, then divide through. The next step is to find your integrating factor. After that, multiply both sides by that integrating factor. Then this is just a little proof. All you really have to do from this step is go on to this step where you write down d dx of your integrating factor, right? That's your mu right there, times y. And then when you integrate the left side, they just cancel, leaving you that integrating factor times y. That's where this came from. That was your integrating factor there. There's your y. And then the right-hand side, you just integrate as well. Do whatever algebraic simplifying you need to do here. Don't integrate those separately, right? That's a times, not a plus. And then you should be okay. If you've got initial conditions, solve for C, plug in, find your particular solution. And this is how you do a non-separable differential equation with an integrating factor. I hope that this example has clarified some of your questions, and you have enjoyed this experience. Thank you.